Okay, so this is the graphical approach to finding solutions. And so I did ask that you have a ruler and a straight edge, or and a piece of graph paper. So a system of two equations and two unknowns can have exactly one solution, more than one solution, or no solution. And by the graphical method, we can gain some insight in about the number of solutions as we look at it. And so when we have a line, that's awesome. Sometimes we'll also have curves as we go through this. And so then just here's a couple of pictures. So, we already went through that little, reminder of ways that curves and lines can be intersecting. These two lines intersect. This curve and a line intersect twice, and no intersection as we look at it. So now our job now is to solve this system, and notice that one of our systems is a logarithmic function. And so we can be asked to graph anything that we have experience with. And so I will give a little time to y equals the ln of x. And so think about what that means. If I rewrite that in exponential form, I'll write ln x equals y. That means, what is the base? E. E is the base. And so e to the y is equal to x. And so when I make a table of values, maybe x, y values to get some things, it's really y I'm going to choose, and then find some matching x coordinates that go with that. And I'm just going to go like -1, -1, 0, 1, 2. That'll give me a good enough -1, 0, 1, maybe 2. So this is, if y is -1, e to the -1 is 1 over e. 1 over 2.7, it's about 1/3, right? And so that means really if x is about 1/3, then y is -1. So I'll just plot a little point there. The next one, if y is 0, e to the 0 is 1. And so that means when x is 1, y is 0. And when y is 1, e to the 1 is equal to x, so that's about 2.7. So when x is 2.7, 2.7, then y is 1. And, probably that's enough. 1 over e squared, I don't know what 2.7 squared is. But that should be kind of a good enough reminder that y equals e to the x. Oh, and I kind of missed that. What is it? 7.3. So I maybe didn't go up to 2. Yes. No, it doesn't. Yeah, 1, 2, 3. I kind of lost that point. So what was it? Say it again. 7.3, and that's at 2. So I can try to, oh yeah, well that's as good as that's going to go. And so then our other curve, x plus y equals 1, x plus y equals 1. So y is -x plus 1. What's the y-intercept? I'm going to graph this linear equation. What's the y-intercept? 1. The y-intercept is b. Y equals mx plus b, and it's 1. And what's the slope? -1. And so I can be at 1, and then my slope is -1. And so you can graph that, and then we get this. And in this case, the line just intersected right at one of our kind of grid points that we've found. So that makes it a little bit easier. So the graphical approach kind of works best if it's going to intersect at a grid point sometimes, but it can still give us an idea of what's happening when we're going to solve these, algebraically as we go. So our solution is at 1, 0, that common point that they have. And just another kind of comment is as we move on, we'll also be graphing inequalities. And when we do inequalities, which with the shading and the solid lines or dashed lines, then we only do that graphically as we go through. So then our next problem is a cost and revenue problem. And so I will find that here. Here we go. We have an application problem. And so here it is. The total cost C of producing X units of a product typically has two components, the initial cost and the cost per unit. So the initial cost would be that like y-intercept, and the cost per unit would be that slope concept as we look at it. So when enough units have been sold so that the total cost or total revenue equals the total cost, the sales are said to have reached a break-even point. So if we have two equations, two unknowns, a cost equation and a revenue equation, where they intersect would be our break-even point. And so in a business that's an important excuse me, point to kind of be able to see where that is. So a shoe company invests $300,000 in equipment to produce a new line of athletic footwear. Each pair of shoes costs $5 to produce and sells for $60. And how many pairs of shoes must the company sell to break even? And so we're going to do this as, a cost and revenue problem. So what their cost is going to be, we'll call it C. What are their costs? Yes. Yep. So 5x plus 300,000. So that initial investment of $300,000 and then $5 per pair of shoes. And then our revenue R is equal to what? 60x. 60x. And, maybe I should slide these this way. And they are constant, but I'm going to change them into y equals equations just so that we have that. And so how would you figure this out? Yep, plug 60x in for y on the top one, so we're going to put that in there. So 60x equals 5x plus 300,000. No. And then we'll subtract 5x, minus 5x, minus 5x, and we get 55x equals 300,000. I think I have the right number of zeros. And then what are we going to do? Divide by 55. And what is the break-even? 5455. And so what does that mean? And then they start making money. Yeah. So then that's when this is going to be the way to we're X is our number of pairs of shoes because we generally sell shoes in pairs. Although well, they just buy pairs of shoes a lot of times. And so the real issue is when you're Most people do not have the exact same size feet. 2 feet. Yeah, that is true. And yeah, yeah, that is true. Yeah. Um, okay. Wow. Okay, so here is one for you to do. And I'll give you a piece of paper and you can have at it. A piece of paper. Okay, there it is. You are, huh? You can do this on this sheet of paper. No, I don't even, was there a survey on there? I don't know. I will pause this and then I'll start it back up after. Okay. So yes, I'm moving along. So then we just had time to do this one, and then it took 4 weeks. So our next section is on solving systems using the elimination method, which is the real method that we probably use most often. And so what I'd like to do is I'd like to get a little start on that, and then I would like to give you some work time today. So that, we have 2 people testing, that way it'll be a little quiet. But we'll get a start on this because, as I said, these are all kind of review topics, so I would like to push a little further than my schedule says at the moment, if we can. You've had a bunch of break days, remember? So, like on Wednesday, we were supposed to be on 7-3. Yeah. Well, okay, right. Okay. So this is the elimination method, and we're going to use the method of an elimination to solve systems of linear equations in 2 variables. You should already be kind of good at this, but we want to really kind of just practice it a little bit so that when we have more equations and more unknowns, that we know what to do as we go. And interpret graphically the number of solutions in 2 variables and use, and we've already talked about this, right? 2 linear equations, they are either intersecting with one, parallel with none, or everything is the same. And and it's an infinite number of solutions, but it's not any number that will work. It's just the ones that are along that common line. And then use systems to model and solve. This is kind of the linear programming. You've probably done it, maybe you haven't called it that, I don't know. So this is the method of elimination. I should be able to go through that kind of quickly, and the method of elimination, we have 2 equations. In this case, if I add these 2 equations, the x's will drop out and I get 3y equals 6, so y is going to equal 2, and then I can back substitute and find what the other one is. But generally, do you agree that in elimination, we're not that lucky? A lot of times we have to multiply the 2 equations by something to make it so that something will go out of that. So here's the method of elimination, and we really want to fine-tune this, and we do want to show our work, and here's why. Because as soon as we learn how to do this method of elimination with linear equations, we're going to have 3 equations and 3 unknowns, 4 equations and 4 unknowns, 5 equations and 5 unknowns. So our process is going to be similar, but right now, and I just want to say that we want to really, kind of firm up and just, make this something that we're really good at. So the nice thing about elimination is it works for pretty much everything. And we do the following steps. Step one, we obtain coefficients for x or y that differ only in sign by multiplying one of the terms, or the terms of one or both equations by a number constant. We add the two equations to eliminate one variable. We solve for that variable, and then we back substitute. And then, as always, we want to check so that we know that we have that correct. So do you remember what happens if it's going to be parallel or the same line? It's it's kind of which one? Which one is infinitely many? It's 0 equals 0. If you get the same number or the something that's equal, it's infinitely many. If you get something that's not equal, like 0 equals -8 or whatever you just said, then they're what? Parallel. Okay, so here's our equation, and maybe we won't even start with this one. Maybe we should start with one that we have to do a little more work for. What do you think? You tell me. Do it? Okay. So 3x plus 2y equals 4. 5x minus 2y equals 12. These are going to eliminate right away. We're going to take e1 plus e2. Listen to the terms that I'm saying because we'll be doing this as we go on. And Cody, go ahead and add those two together and tell me what you get. And then solve. X equals 2. And then we're going to back substitute. Isaac, what do you want to back substitute into? Okay. And what do you... Y equals -1. And 2, -1. And then we'll just do our quick check. 3 times 2 plus 2 times -1. 6 minus 2 is 4. And then 5 times 2 minus 2 times -1. 10 minus, or plus 2, excuse me, is 12. And so it checks in both of those. And it all works just wonderfully as we go. So here's our next one, and let me find it. Oh, just kidding. There it is. You're noticing they're labeling these as equation 1 and equation 2. We're going to start saying that that's E1 and E2. And so when we get into more involved problems, we're actually going to say what we're doing. So I'm going to kind of start modeling that. In my mind, do you agree that I would multiply E2 by 4 and then add the two together? Okay, so I'm really going to do E1 plus 4E2. Do you agree? And that's going to be my little code because, and I feel like I didn't write that very well, or it looks funny. And that's going to be my little code because I'm going to forewarn you that as we get multiple variables, multiple equations, it becomes very easy to make little mistakes, and so then we just want to know that this is what we intended to do, and that helps me give you credit when you're doing things. So 2x minus 4y equals -7. Danae, go ahead and multiply that by 4 for us. Okay, and then Jared, go ahead and tell me what I get. We're going to add these two together now. I'm going to leave that out then. Equals -11. And Claire, what are we going to do next? And what is x going to equal then? So, a little less desirable, but not a super issue for us. Cody, where would you like to back substitute? There is a preferable one. All right, I would agree. So go ahead and do that for me. Okay. And which is okay. So um, negative 1/2, 3/2, and we will check. So we go 2 times negative 1/2 minus 4 times 3/2, and so this is -1. This is, was that a 3? Minus 6, and that's -7, so that one checks. This one, 5 times negative 1/2 plus 3/2, and this is -5/2 plus 3/2, -2, or -2/2, which is -1. And so that one checks as well. So what I'm going to do is I'm going to give you some working time. I expect it to be library-like quiet, and you have some time. These are not difficult things, but I do want you to do some practice on them, and I will give some time right now since we have people testing. The homework check for 7-1 is not until Tuesday, and so I will let you use some time to do that.